So how do we find roots of polynomials? Well, there's various tools that we can use in our process of finding roots, and here are a few of them. The first one, and I think that most students remember the quadratic equation, or at least remember that there is something called the quadratic equation. This is a great tool. If you have a quadratic polynomial, the quadratic equation just gives you the roots. So students should make sure to remember and memorize the quadratic equation. Okay, second tool. This is called the Factor Theorem, or at least this is what I prefer to call it. And students sometimes know this by different names. But here's the idea, and that is if you have a number that's a root of a polynomial, then x minus that number is a factor of that polynomial. So this is a basic fact about algebra. This should be a part of any Algebra 1 or 2 class. Algebra 2 at a minimum. And hopefully students have seen this before, perhaps under a different name, and if so, that's fine. I think it's a good idea for students to know how to prove this. I have the proof written up in a short PDF document on the class webpage. It's not a hard proof. It's accessible to a high school algebra student, really. And students should take a look and make sure to understand why this is true. So the idea then is if you're looking for roots, very often you can find those roots by finding factors. Right, so our attempt to find these roots is going to boil down very often to factoring the polynomial. Okay. All right. Now here's one you might not have seen. I think most students have not seen this before. It's called the rational root theorem. You have a polynomial, and there's some requirements now on this polynomial. It can't just be any polynomial. It has to have integer coefficients, all integer coefficients. If there are some rational coefficients, well, then you have to multiply by whatever factor is necessary to make all of the coefficients integers. Okay. Secondly, if this polynomial has integer coefficients, suppose that you have a rational root. Now, that's another if. We're not saying that this polynomial has a rational root. There are plenty of polynomials that have no rational roots, to which, therefore, this rational root theorem does not apply at all. But if there is a rational root, and keep in mind a rational number is a ratio of two integers, right? So write down the P over Q for that particular rational root. By the way, make sure that P and Q have no common factors, so this has to be a reduced fraction. And the amazing fact is that this numerator has to be a factor of A naught, and this denominator has to be a factor of AN. Okay. We'll see some examples of how to use this in a few minutes. Roughly speaking, the idea, though, and we were going to make use of this is we find ourselves looking at a polynomial. We can write down, by looking at the various factors of that number and the various factors of this number, we can write down a short list of all of the possible rational roots. Now, again, no promises that any of them actually will be, but if there are any rational roots to be found, they will be on that list. Okay, so they're good candidates. Next, polynomial division. You have a polynomial that has a factor of x minus a, and you can just divide. Just take this x minus a and divide it into p of x by means of this method called polynomial division. We'll see an example of it in just a minute. And we can then get a quotient q of x. Now, why do we care about this? Well, very conveniently, if you find a root of q of x, well, if q of x is equal to 0, that would mean that p of x is also equal to 0, and that means that you have also found a root of p. So anytime you find a root here, you've also found a root here. And the good news is that this is a lower order polynomial. Say this is perhaps a fourth order polynomial. Well, then this is only cubic. And it's easier to work with. And yet all the roots that you find there are also roots here. Okay, nice tool. Lastly, and this one doesn't come up very often, but if you have two values of a function that have opposite signs, then there's got to be a root somewhere in between those two values. And it's just a quick observation, and every so often this is useful. Okay, let's see how polynomial division works. This method right here. How is it that you actually take x minus a and divide it into p of x? All right, well, it's actually a lot like long division that I hope and presume that y'all have seen back in elementary school. In fact, maybe so long ago you might not even remember exactly how to do it. But here's the idea. So this has x minus 2 as a factor, and if I want to know what is this quotient, then I take my numerator there, this my denominator that I want to divide it by, I put it there, and I play this familiar game. I ask first, how many times does this go into there? Well, that's kind of the whole point, is to figure that out, and that's hard to say. So conveniently, instead, we can ask, well, how many times does this go into there? And we'll worry about all the lower order stuff later. So x goes into x to the fourth x cubed times. Okay, so we write that down. Having written that down, I then multiply that times this to get that, and then subtract. And what's left over is minus 2x cubed. Okay. All right, and then repeat. How many times does x go into minus 2x cubed? Well, it goes in minus 2x squared times. Okay, then we take minus 2x squared, multiply that by that. That gives me that, which I then, subtract. Okay. Don't forget, of course, to constantly bring down the other stuff that's waiting. Okay, just like in long division. Okay, now continuing, how many times does x go into 5x squared? Well, 5x times, take this, multiply by that, and get this, subtract, bring down, and the process continues. And conveniently, in the very last step, how many times does x go into 3x? Well, 3, and that 3 times x minus 2 gives you exactly the 3x minus 6 that you had above, and so when you subtract, you get 0. So what you see is that there's nothing left over. The remainder is 0. Okay, so it's just like elementary school division. In fact, you can see it's fairly transparent how this thing works. When you write down x cubed, you're just keeping track of, the whole idea is that this, we want this times that to add up to this. And we just keep track of how much we're contributing. This contributes that much. This contributes that much in that product. This contributes that much. And lastly, this contributes that much. And having subtracted these things off, what I've in fact confirmed is that when multiplying this times that, altogether it has added up to what it was supposed to add up to. So like I say, it's a very transparent method. It's very clear why this works. Okay, now I am aware of the fact that lots of students have seen a method called synthetic division. A lot of high schools teach this method. It will allow you to find the quotient. The trouble is, very few, if any, students understand why it works. It's not immediately transparent as to why it works. There are good reasons, but students, if they don't understand the method, then it's just a mechanical calculator, basically. And in this course, we want students to demonstrate ideas that they understand and not to go through little hocus-pocus games that will allow them to get an answer that they don't know where it came from. So synthetic division, very importantly, not allowed in this course. On an exam, if you use synthetic division, you will not get credit for that work. So be sure that you do not use synthetic division. Instead, use this polynomial division per the example that we just saw. Okay. All right, so let's put all these ideas together now about finding roots of polynomials, and let's solve some differential equations. Here's one. There's a differential equation. Really not immediately obvious at a glance what would be a solution, at least not until you see what the solutions are. You know, hindsight being 20/20, etc. So how do we solve this? Well, an earlier observation is that what we really need to do is to find roots of the characteristic polynomial. And remember, the way we find roots of the characteristic the way we find the characteristic polynomial is derivatives become factors of lambda. Here we have one derivative, therefore one factor of lambda. Two derivatives, two factors of lambda. Here there were no derivatives, so no factors of lambda. Okay. The coefficients all come along for the ride. There is a very common mistake that students make, perhaps because lambdas look like an upside down y, and so very often students will write down here a lambda that's not supposed to be there. Just be careful about that. Lots of people have done this, and it's an easy mistake to make, and just make sure that you don't. Okay. So there's our characteristic polynomial. We'll want to find the roots. You can find the roots of this polynomial in a couple of different ways. One thing you could do is use the quadratic equation, or you can play the guess and check game for roots of quadratic polynomial. That it's not a hard game to play. You're trying to find two numbers that multiply to that and that add up to this. Right? Hope you can get lucky. In this case, it's not hard to do that. This is how they factor. Therefore, these are the roots. Once you know the roots, keep in mind the purpose of the roots is that those are the exponent coefficients of the corresponding solutions. So there we go. We found two solutions. Okay. We basically guessed, but this is a highly educated, clever form of guessing, and we guessed right. Okay, now these two functions are independent because they're not multiples of each other, and that's one of the nice things about a list of two vectors. Two vectors are independent if and only if they're not multiples of each other. Neither one is a multiple of the other. So they're clearly independent. And we can make our linear algebra arguments. We have a two-dimensional vector space of solutions. This is an independent list of two vectors. Therefore, it's a basis. And therefore, we have here a fundamental set of solutions. And we are completely done then with this differential equation. We have found not only all of the solutions, but we know that is all and that there are no more. Okay, now that was an easy one. Let's do a harder one. Let's solve this fourth order constant coefficient linear differential equation. Again, homogeneous only for the moment. We'll talk about non-homogeneous later. Okay, well, characteristic polynomial. 4 derivatives becomes 4 factors of lambda. 3 derivatives becomes 3 factors of lambda. Coefficients come along for the ride as usual, and etc. Okay, so here's our characteristic polynomial. How in the world are we going to factor and find the roots, therefore, of this characteristic polynomial? This is where the rational root theorem is going to be extremely helpful. The rational root theorem gives us a list of candidates. So here they are. Here's our candidates. Keep in mind we have to look at factors of negative 28 and then divide by factors of, well, the coefficient over here is 1, so then we're looking for factors of 1. So how many factors does 28 have? How many factors does 1 have? And let's start, writing down their fractions. Now, conveniently, 1 has no factors other than 1. So all of our denominators are going to be 1. So that's nice. So really, I just have to write down the various factors of negative 28. And here they are: plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 7. Let's see here, plus or minus 14, and plus or minus 28. That's it. Right? Those are the only factors. So that means if there are any rational roots, it's got to be off of this list. So how about this? How about we just start trying the numbers on this list? We don't have any better ideas, so let's start following these leads. So let's start with plus 1. Plug that into the polynomial. Does it work? Nope, didn't work. And do the arithmetic, plug in lambda equals 1, and highly negative value. Clearly we didn't get a root. Okay, so that was not a root. Okay, let's try negative 1. Does that work? Take that, plug it in. What do you get? Well, there's some arithmetic to be done here, but when you add it all up, yes, that works. Negative 1 is a root. So we found a root. Good deal. 3 more to go. But we found a root. Having found a root, we can divide. This being a root, we know that's a factor. We can then do long division. Long divide that into there. The quotient becomes this. And now we can focus our attention on this cubic. I no longer have to deal with the quartic. I can just look at the cubic. All right. So can I find roots of this cubic? All right. Well, rational root theorem again applies, and conveniently these coefficients are still the same, and so we still have the same candidates. And well, here we go. We have to start trying these numbers again. Now, what about plus 1? Is there any chance that that's going to work? I've already tried it, is the thing. And I've already found that it failed. It can't possibly work here, because if this were equal to 0, if this factor were equal to 0, then it would follow, if that were equal to 0, that that would have to equal to 0, but it wasn't. Right? Plus 1 simply didn't work there. Therefore, 1 cannot work here. So, plus 1, I don't have to try that. Don't even bother. It's wasted arithmetic. All right. Okay, what about negative 1? Do I have to try that? There's a temptation to say, no, I've already tried that one as well. The thing is, it worked. So it was a root. Therefore, this polynomial did have a factor of lambda plus 1. The fact that there is a factor of lambda plus 1, that does not eliminate the possibility that this might also have a factor of lambda plus 1 as well. Right? A polynomial can have multiple copies of the same factor. So the negative 1 I do have to try. I do have to plug that in and see what I get. And unfortunately it doesn't work. Okay, all right, well, nevertheless we had to try it. Okay, so then you try 2. And then you keep going. You try negative 2. You keep trying things until you run out of things to try. The good news is that 2 does work. 2 is a root. That's arithmetic you guys can confirm for yourselves. Therefore, lambda minus 2 is a factor, which you can long divide. The quotient ends up being this. Now notice we've made a lot of progress here. We had been dealing with a quartic, and now we've got it down to just dealing with a quadratic. Quadratics are easy to factor. This quadratic factors like that. Again, you can quadratic equation if you like, or you can play the guess and check game, which is a little easier in this case. So all together then, don't forget the first factor we found was lambda plus 1. The next factor we found was lambda minus 2. The remaining quadratic quotient factored like this. So that's the complete factorization of that quartic. That gives us 4 roots. Each root gives us a corresponding solution. Don't forget the minus signs. And we have then 4 solutions. Now, here's where we begin linear algebra games. We had a 4-dimensional set of solutions because it was a fourth order equation. We have here 4 solutions. I'm going to assert here for the moment that these are independent. And that is true, they are independent. We'll talk about how I know that later. And therefore, by linear algebra arguments, this is a basis and thus a fundamental set of solutions for our solution set.